Let me start to share my solution. This is the agenda for my presentation. Firstly, background, and then overview, training method, inference method, and finally, what I learned. This is my background. Sorry. My academic background is in complex system, especially theory of deep neural networks and kernel methods. In terms of my experience, I have worked on a few image competitions, and this time's solution is based on a 3D convex approach that was implemented at RSNA 2024. Here is an outline of my pipeline. On the training side, I began with mask generation to localize region of interest, followed by normalization and patch-based preprocessing. I used unit architecture with a convex style encoder and trained it using a binary cross entropy loss. For local evaluation, I relied on the competition's official metric. For inference, I normalized and patched the image, then combined the outputs of my 7 highest performing models on the public leaderboard through an ensemble with test time augmentation. Finally, post-processing steps utilized connected component analysis via CC3D and DB-scan to refine centroid predictions. From here, I will explain training method. Initially, the public baseline adopted a uniform approach using R time 0.8 for all particles as ground truth mask. I adjusted this by applying different scaling factors for each protein complex as shown in the table. For example, instead of using R time 0.8 for ribosomes, I used a factor of R divided by 3 to define the mask radius. This adjusting helped capture the true point more accurately, and it led to a performance gain of roughly 0.02 to 0.04 on both the public and private leaderboards. This is the preprocessing for training. I performed value clipping at the first and 99th percentiles and then normalized each volume to a 0 to 1 range. For patch-based training, I used a patch size of 32 by 256 by 256. We in V, Y, and X respectively, with an overlap of 8 by 69 by 69 to ensure a smooth coverage of the entire volume. This is the training overview. I implemented a 3D unit with a convex-like encoder and replacing the traditional double convolution blocks to convex-like convolution module for decoder, because convex is faster and high performance. Finally, binary cross entropy loss was used for each particle segmentation output. Architecture is here. Here is the details of model. To adapt convex for small particle segmentation, I use the 2x2 stem instead of the original 4x4, since a large stem can obscure fine details. I also replaced the 7x7 depth-wise convolution with a 3x3 kernel and reduced the layer configuration from 3393 to 3333 for limiting parameters. For the decoder, I utilized the same convolution module as encoder and used an upsample for upsampling. From here, I explain inference methods. During inference, I used a slightly larger patch size of this, with an overlap of 6 by 10 by 10. This change compared to the training setup was made to reduce inference time, because the total number of patches is reduced from 72 to 28. Here is the TTA and ensemble method. For TTA, I use the original patch plus its 3 rotated versions as additional batch. I then assembled the prediction from my top 7 models, averaging their output to yield the final segmentation. This is post-processing. I used CC3D with connectivity equal 6 instead of the default 26. And also, finally, I refined centroids via DV scan, which added a further 0.001 improvement. Finally, this is what I learned. Throughout this competition, I discovered the importance of understanding the characteristics of dataset and incorporating the model architecture accordingly. Next, generating ground truth in alignment with the evaluation metric is essential for optimizing performance. Finally, I learned a lot of methods for accelerating inference speed. That is all of my presentation. Thank you.